Okay, hi Math 30-1. So today we're going to actually look at radical expressions. So to start with, properties of radical expressions, a radical function has the form y equals root f at x. So we will only be looking at radical functions which are square roots. So we won't be looking at any other radical functions with any other type of index, just square roots. So f at x is a function, and the square root of a number is only defined by non-negative numbers. So really, you can't have any negative y values. The reason being is we cannot have a negative radicand, and hopefully you kind of remember that from Math 20-1. So if you were given an original graph and you were asked to draw the radical of that graph, the first thing you would start with would be your invariant points. Okay, so if I were to square root 0, I'd end up with 0. So anytime y equals 0, I will have an invariant point. If I were to square root 1, I'd end up with 1. So anytime y equals 1, I will have an invariant point. So what I'm going to do is I'm going to draw those invariant points on my graph. So here's where y equals 0, and y equals 1 about right here. Now that I have my invariant points, what I can do is I can take any value and square root it, any of my y values. So if I were to take 6 and square root 6, and I can even type it in my calculator, I would end up with 2.44. So I'd end up about right here. I can't have any negative values because we can't have a negative square root, so we can't have any negative y values. So that means my new graph is going to look something like this. So when I try to write the domain and range, I will notice that the domain, is extending from -3 to the right. So my domain, and again, you could write this in interval notation instead of set notation if you wanted to. You would just say x is greater than or equal to -3, where x is an element of all real numbers. If you wanted to write the range, in this case, because you can't extend into those negative y values, my range is actually just going to be y is greater than or equal to 0, where y is an element of all real numbers. And then I'll do the same thing over here. So with my second graph. So I will start by putting dots where there's invariant points. So there's an invariant point here because that's where y equals 0. And there's another invariant point here because that's where y equals 1. And then I will square root different points of my graph. So the square root of 4 is 2. Okay, here's 9. So the square root of 9 is 3. So my graph is going to look something like this. All right, so now to write my domain and range. So notice how the domain, starts at that x-intercept of, it looks like 5. It kind of looks like I cut a lot of that off there. And it's less than or equal to 5. So I would say x is less than or equal to 5, where x is an element of all real numbers. And then for my range, once again, I would say that y is greater than or equal to 0, where y is an element of all real numbers. Okay, let's look at a couple more examples here. So you're going to start the same way. Let's list all of our invariant points. So y equals 0 here and here. Y equals 1 here and here. So you can see on this graph I actually have 4 invariant points when I take the square root of the graph. And then from there, you're going to extend upwards this direction and then this direction. Okay, so now to write my domain and range, and this time I'm going to write in interval notation instead of set notation. Or actually, no, I think I'll write in set notation again because I have the 2 directions here. So for all x values, I would say that x is less than or equal to -3. Or x is greater than or equal to +1, where x is an element of all real numbers. And then my range, once again, would just be for all y values, y is greater than or equal to 0, where y is an element of all real numbers. That's a 0, not a 6. 0. Okay, so now with my second graph on this page, start the same way. Draw your invariant points. So y equals 0 here at -4, here at the origin, and then I'll draw invariant points where y equals 1. So y equals 1 here and here. And now I can take the square root of any noticeable point. So I'm going to take the vertex here, which is at y equals 4, and I'm going to square root that vertex. The square root of 4 is 2. And now I can draw my graph. There we go. So it's going to look something like that. So then my domain for this graph would be for all x values, x is greater than or equal to -4 and less than or equal to 0, where x is an element of all real numbers. And then my range for all y values would be y is greater than or equal to 0, but you will notice there's a maximum point here. So the maximum point is at 2, even though I didn't do a very good job of drawing that. So my range would actually be that y is greater than or equal to 0 and less than or equal to 2, where y is an element of all real numbers. So that's the general gist when it comes to radicals. So we will look at transformations with radicals as well. So with transformations, it's kind of the same idea. So we're going to actually use root x as our reference point here. So this says the function, we're going to fix that and just do root x. Okay, so if root x was my function, what transformations took place? So notice how the x was replaced with x minus 3. So that means that we are going to be moving right 3 units. I'm actually going to just write 3 units. Notice how my plus 2 is outside of the radical. So that will show a transformation up. So I'm going to go up 2 units. So then my new graph would look something like this. I would move up 2 units and over 3 2 units. And so it'd be something, oh, I didn't do a very good job of that. Let me try that again. Something on the lines of that. Okay, so you could see, and I'm not going to list them for these slides, but your domain and range would also change in this case. So it would change your domain and range. So now my original domain was x is greater than or equal to 0. Now my new, or actually, you know what, I'll list it for this one. My new domain would be that x is greater than or equal to 3. My old range was y is greater than or equal to 0. My new range would be that y is greater than or equal to 2 now. So you can see that those transformations did in fact affect my domain and range. So we won't look at all these examples. Why don't we just look at the last one over here? Okay, so when you're working with transformations, you always want to write in factored form. So I'm going to factor out my -2, which would leave me with x plus 2. Okay, so now when you write your transformations, okay, notice how that -2 would be my b value. So it would be replacing my x. So that is going to show a horizontal stretch and also a reflection. So I have a horizontal stretch of 1/2, right, because you always take the reciprocal, along the x-axis. Oops, sorry, along the y-axis. Whoops. And then because that is a negative, it means I'm also going to have a reflection along the y-axis. Okay, and then the 2 here, that's just going to show a translation left. So I would say left 2 units. Left 2 units. Okay, and you could type this one in your calculator. You could try applying those transformations if you wanted. But our new graph is going to look like this. something along those lines. All right, so we're going to finish off with a couple diploma questions. So it says, sketch the graph of y equals root f at x. So the original function is drawn for you, and we're going to sketch the graph of the square root of that function. So I like to always start with those invariant points, where y equals 0 and where y equals 1. Okay, and then I will gradually go upwards over here. Notice how on the right hand side of the graph here the function levels off at 2. So I do need to take the square root of that 2 so that I know where the radical will level off. So the square root of 2 is 1.4 about. So then my graph should level off at about 1.4. There we go. So my domain of this new graph would be that for all x values, x is less than or equal to -3, or x is greater than or equal to 0, where x is an element of all real numbers. And then my range for my new graph, for all y values, y is greater than or equal to 0, where y is an element of all real numbers. Don't be tricked on the fact that the graph levels off on the right, because on the left you can see that the graph will extend upwards towards infinity, towards positive infinity. So now we're going to determine how many invariant points we have. We already started the question that way, so we had 4 invariant points. Yay, look at the little unicorn. Okay. Here's one more diploma question. So it says the graph of y equals root f at x has a range. So this time, this question is different because this time they actually gave us the radical graph. They didn't give us the original function, they gave us the radical graph. So if f at x is a quadratic function, then a point which cannot be on the graph of y equals f at x is what? So let's pay attention to the information we have. We know the range is from 0 to 9 of this radical graph. So that means the original graph would have to be, if this has a maximum point at 9, the original graph would have to have a maximum point at 81. So it would look something like this, right? You would see those invariant points at 0 and 1, and the highest this graph would go to would be 81. And it would extend downwards towards negative infinity on both the left and the right tail of the graph. So if f at x is a quadratic function, then a point which cannot be on the graph of y equals f at x would have to be C, because I know that my graph will not go any higher than 81. That's it for today. Try some of the workbook questions in your workbook, and I will talk to you soon. So next lesson we're going to learn about rational expressions, so that'll be lots of fun.